The subject is operating system and the topic is process scheduling. Now first we will discuss what is the CPU scheduling, then we will see what is the importance of scheduling in the algorithms. Then we will see the scheduling algorithms like FCFS, first come first serve, and round robin. Now basically the first term, that is the CPU scheduling. What is the CPU scheduling? CPU scheduling is basically nothing but a process scheduling, like how the OS will decide which process will get the CPU. CPU is nothing but the processor. There are some techniques, like suppose we have an n number of jobs. Suppose we have n number is n equals to 4. We have job 1, job 2, job 3, job 4. So who will get the CPU first? So all the technique which will decide that which job will get the CPU is the CPU scheduling. Deciding which thread or a process are given access to the resources from moment to moment. Assumptions, like what we assume about the scheduling. Like since 1970s, we are still researching on this topic, that's CPU scheduling. Now, what are the assumptions? Like one program per user. Like suppose we have a user 1, so it should allocate only one program at a time. One thread per program. As we know, there are n number of threads for a program, so one thread per program should be allocated. Now programs are independent, that means there should be no dependency between the programs. Now next is, these are some unrealistic but simplify the problem is what? Who will get the CPU first? Like next is, what does fair means? Fairness among the users of program. If I run one comparison job, you run 5, so who will get how many times? Suppose I run a job 1 at a time and you are running 5 at a time, so who will get the CPU more time? Suppose I am getting a time at a 1 time, you are getting 1 time. Again, next time my CPU is idle because I have only one job, but you have 5 jobs, so you will get the CPU again and again. So this is all about the, if I run one comparison job and run 5, do you get 5 times as much as CPU? Mostly it is yes. Now some next assumption is the burst time. It is basically, it is a time for which the process will get the CPU. There are 2 times, that is the burst time, and next is the input output time. During the execution of a program, the process or a program will get into 2 states. First is the burst state, when it is actually running on the CPU. Second is the input output time, when it is waiting for some input as in some input from the keyboard. Output, it could be like some output to be shown on the screen, monitor screen. It is a monitor. It could be printer, some print to be printed. So the process involves two times, that is the burst time and the input output time. Burst time, which is exactly the CPU time of a process. Next is the input output time, when the process waits for some input and some output. So basically, see, this time it is CPU time for a single process P1, let's say. So this is the first, it is a CPU time, when the process get the CPU first, load some data, add some data, read some from the file. Next is the IO time, that is when the process is waiting for some input output. Next, in the CPU time, when it actually gets the hardware, it stores some data into the registers, then increment the value and add to the file. This is the CPU time. Then again it will go for the input output. So basically this is the alternate cycle. First the process will get the CPU, then input output, then CPU, input output, CPU, input output. So the process first will get the CPU, then it will get the input output, and so on. So this is the alternate cycle between the CPU burst time and the input output burst time. See, this is the graph for this. Is the frequency between the burst time. How much time the CPU will get the process will get the CPU. Assumptions. C. Program typically use the CPU for the second period of time, then does input output and CPU again. As I already told you in this slide, in the last slide, first it will get the CPU, then it will get the input output, then it will get the CPU, input output, CPU, input alternatively. This line suggests that typically uses the CPU for some period of time, some time, here it is some time, then does the input output wait, here it is, then uses the CPU again here. Each scheduling decision is about which job to give the CPU for use by the next CPU time. That means when the CPU will leave when the process will leave the input output this stage, for the next time for the next CPU time, which job will give to the CPU. This is all about the CPU scheduling. There are some methods or we can say some strategy or algorithms to decide which job will get the CPU first. Like we can say FCFS. It works like a queue. FIFO. FCFS is nothing but the first come first serve. Who will come first will get the CPU first. That means who will get first in and first out. Next is the round robin. It works like a time sharing environment. That means there is a time slice and the processor, that CPU, will divide its complete processing into some time. Suppose it is a time slice is 2 seconds. For the current 2 seconds, the CPU will be allocated to the J1. For the next 2 seconds, it will be allocated to job 2. The next 3 seconds, it will be allocated to job 3, and so on. So the whole processing time of a CPU will divide into some time slice according to the given time slice. It is all about the round robin. We will see this in detail. When the time slicing, thread may be forced to give to the CPU before finishing current CPU burst. Now see why it is important in a scheduling algorithm. हमें scheduling algorithm जरूरत क्यों है? Why it is so important for a scheduling algorithm to allocate the processor for given jobs, like job 1, job 2, job 3, job 4. See why it is important. The first point is minimize response time. Now let's see what is the response time. What is the response time? Response time is the time when the job or some process will get the CPU first time. Suppose it is a timeline, and at this time it is 0, it is 1, it is 2, suppose, and maybe so on. Job J1 arrived at time 1 here. Here job J1 is arrived, but it get the CPU at time 2. Maybe some other process is already running in this particular CPU time. Some job J2, suppose. So job J1 get the CPU at time 2. So for now, when it is arrived at 1, but CPU is allocated at time 2, that means response time is 1 second. That means CPU took 1 second for job 1 to allocate the processor CPU. Next is the C. Elapsed time to do an operation. Response time is what the user sees. Time to echo keystroke in editor, time to compile a program, maybe compiling a program, real-time task, must deadline imposed by a world. Okay? When the process will get the CPU first, it is the response time. When actually CPU responds to the particular job. Next is the maximize throughput. What it does, what it means, throughput is nothing but for a particular amount of time, how many jobs are allocated to a CPU or completed their processing time. That means job per second. It could be some other unit like millisecond, maybe hour, maybe something else. throughput related to the response time but not identical. Maybe it is related to the response time when it is first related to the CPU but not the same one. Minimizing response time will lead to more context switching than if you maximize only throughput. That means what it says, if I want to minimize the response time, if I want to minimize the response time, it will basically increases the context switching. Now the term called a context switching. What it is? There's a term called a context switching. What it is? See, this is the CPU unit. For time 0 to 1, it is allocated to job J1. For the time 1 to 2, it is allocated to job 2. The scenario. See, so for the job J1 or a process P1 or a J1, let's say, there is a term called a PCB for this particular job, and also for this particular job there is a PCB. This is the process control block. PCB stands for process control block. So whenever a job or a process wants to execute in the CPU time, or want to execute the CPU is program in the CPU time, it is allocated to the main memory first. That means all the pointers, all the related files, documents, and all other things should be loaded in the main memory. Suppose at this time job J1 left the CPU, so from the main memory to the second memory should be placed, and now the PCB of job J2 should be in the main memory now at this particular time. So from placing the PCB of job J1 to secondary memory and placing the main memory PCB of job J2 in the main memory, this whole process is called the context switching. That means job J1 is going to the secondary memory because this is preempted. Now job J2 is getting the CPU at this time, so this will be should be in the main memory. So loading all the details regarding related to the job J2 should be in the main memory. That means it should be the PCB details. This control block. This contains the pointer of the next, pointing to the next job to be executed. Next is the all file, related files, registers, memory space, like some software requirement, hardware requirement. So this is the content of PCB. So this should be in the main memory when this particular process wants to execute in the CPU time. See, if I want to minimize the response time, it will eventually increase in the context switching. We just see. Now minimize overhead. That means if I want to minimize this context switching time, or this is actually an overhead only. So it will basically maximize the throughput. Done. Next is, now see the first CPU scheduling, that is the FCFS, that is a first come first serve, or FIFO we can say, like a queue. Who will get in first will get out first. First in, first out. So run until done. जब तक वो complete ना हो जाए. That means it is a FIFO algorithm. Now the first key point about the FIFO is FCFS is it is always non-preemptive in nature. Now see the term preemptive, non-preemptive. Non-preemption means when a process or a job allocated to a CPU, it will not leave the CPU in between. Like maybe job J1 is allocated to the CPU. Okay, it needs some input output, but it will not leave the CPU in between. Okay, this is about the non-preemptive. But if any particular algorithm or a process is preemptive, that means it can leave the CPU in between. for the waiting time. Suppose job J2 is in the CPU and it is a primitive. It is primitive. So it can leave the CPU whenever a new process with the higher priority will come in the queue or some other things like. So let's see the FC. It is always non-preemptive. That means it will not leave the CPU until it is done. Now in the beginning, this means one program runs non-preemptive until it is finished. As I already mentioned, what is a non-preemptive? Until it is finished. Okay? Including any blocking for input output. That means if a process wants to do some input output operations, it will be have to in the CPU time only. It will not leave the CPU in between. Now FCFS means first come first serve, means that a process keeps the CPU until one or more threads block. Okay, done. Now let's see this particular algorithm with an example. Example is, suppose we have a three process arise in the order P1, P2 and P3. Now there is a term called a arrival time, in which time duration in which sequence they arrived in the ready queue for the processing. Suppose P1 arrived at time 0, it is 1, it is 2, and it is already mentioned in the example. Three process arrives in the order. Order means sequence. P1 will come P1 came first, next P2, then next P3. Now see the burst time. The time actually it is required of CPU time, right? See, it is P1 required CPU time 24, P2 required CPU time 3, now P3 required CPU time 3. Clear? See, now the arrival time of these three processes are 0, 1 and 2. It is clear? This is given in the example. Now see, what is the question here? Draw the Gantt chart and compute average waiting time and average completion time or the exit time. See the first, what is the waiting time? The time process P1 is arrived in the ready queue. It is arrived. Suppose P1 at 0, but the CPU is busy. The CPU is not allocated to the P1, so it is waiting to some particular time. This time is called as a waiting time. Suppose P2 is arrived at time 1, but it gets the CPU at time 2. So for this particular process P2, the waiting time is 1 second, right? Next is the average completion time. What it is? The time at which the process leaves the CPU. Suppose it is 4. It is done, it is completed. Now the completion time for the particular process is this 4. When it actually leaves the CPU after completing all this its processing. Now, this example. Three processes arrive in the order P1, P2 and P3. See, P1 as already seen in the last slide, P1 burst time is 24. It is 3. It is 3. Now P1 arrives at it is initially 0. So P1 will get the CPU first for the complete processing of this burst time. See, it is 24. So for the next 24 seconds, the CPU is allocated to P1 only. Since there is a non-preemption, that means it will not leave the CPU until it finishes. Take from 0 to 24, the CPU is allocated to P1 only. Now P2 arrived next with burst time 3. So from 24 to 27, P2 is allocated to CPU. It is. Now P3 arrived last with a burst time 3. So this is the CPU time of P3 from 27 to 30. Right? See. Suppose P1, P2 and P3 all arrived at 0, but with the order. That means P1 first, P2 this, and P3 at this order. Now see the waiting time of each process. Suppose the process P1 at arrived time 0 and get the CPU at time 0 only. So for the P1, the waiting time is 0, right? Now see the process P2. P2 arrived at time 0, right? But after the P1, but get the CPU at 24. So it actually waits from 0 to 27. See, so the waiting time for P2 is 24. Now see the P3. P3 arrived at time 0, but gets the first time CPU at 27, response time 27 actually. See, arrived at 0 and get the CPU 27. The waiting time for the P3 is 27. In the last slide, it is asking for the average waiting time. That means sum of all this divided by 3. What it is? See, it is 17. This is the average waiting time. Sum of all the waiting time divided by 3. Why 3? Because we have 3 processes, P1, P2 and P3. Now see the completion time. When it actually leaves the CPU, it is also called as the exit time. See, P1 exit the CPU or leaves the CPU 24. So the completion time of P1 is 24. P2 leaves the CPU 27. So the completion time for the P2 is 27. P3 leaves the CPU, this is the CPU, at 30. So the completion time for P3 is 30. Then now calculate the average. Average, that means sum of all this divided by 3. It is average completion time, that is 24, 27, 30 divided by 3, 27. So this is all about the waiting time and the completion time. Suppose what if their order had been P2, P3 and P1? We will see this in the next lecture. Thank you.